Okay, so starting things off for Retro and the Space Challenges Group, I'm Chris Lewicki, President and Chief Asteroid Miner at Planetary Resources, and today is November 2013, and I'm going to give you a brief overview of what the company is working on today and what our vision for the future involving space resources is. I'll share the story with you for about 30 minutes or so. To start with, Planetary Resources' mission and vision is to expand the economic sphere of influence of humanity off the surface of the Earth and into the solar system. We believe that all of the frontiers that we've opened up here on Earth have been a result of pushing into new frontiers, using resources, and sometimes actually in pursuit of resources, in the case of gold rush in California, as an example. But asteroid mining and space resources, of course, is a very big idea, and in getting an entire industry started, we need some stepping stones along the way. And in any mining venture, often that first activity is in the prospecting. So our current focus and what we've staffed the company up, what we've raised funds for, and what we're pursuing every day is the identification, prospecting, and claiming of near-Earth asteroids for all of the resources that are on them, from fuels to industrial metals, and we'll talk more about that as we go. Back to the story. The team we've assembled of engineers and business people, scientists and entrepreneurs at Planetary Resources really is world class. I was the first one in after I'd spent about 10 years at the Jet Propulsion Laboratory. Met Raicho here with Space Challenges when I spent some time at the Singularity University as a faculty member and learned a lot there. And with me, I've brought with engineers like Chris Voorhees, you see on the screen here, who is the chief engineer for the Curiosity rover and also designed the mobility system on Spirit and Opportunity. We have other folks who have kind of similar levels of experience, but we're also looking outside of the typical space experience and looking for just good engineers who've worked in different product life cycles. So Ray leads up our avionics team, and he was central in the CPU architect team at Intel for creating the Core i7. Frank is with our business team, and he's been, as well as being an engineer, he's been through all sorts of things. And then, of course, people are probably familiar with Peter Diamandis and Eric Anderson, who are the co-founders and co-chairmen of the company. And they are the reason why we're pursuing many of these entrepreneurial aspects in space, and it's a pleasure to have them on board with the founding and with the leadership in Planetary Resources. But of course, none of this would be possible without the investors, and we've had the great privilege to have a number of not only very wealthy but very successful businessmen, entrepreneurs, and visionaries involved in our company. So this has been headline making, of course, in terms of the number of people who've gotten involved. But for me, it's really more about their perspective on doing things that have never been done before and taking risks and really thinking big, hairy, audacious goals. And Ram Shriram in particular was one of the earliest investors in Google, and we were with him as he was doing an interview for the New York Times, and he was asked by the New York Times reporter, Ram, why would you invest in an asteroid mining company? What if it fails? And without skipping a beat, he turned the question around and said back to them, well, what if it succeeds? And this is really the viewpoint that all of these gentlemen have, is that this is something that, when successful, will really change the way not only that we live and operate in space, but will do so for all the activity right here back on Earth. We've also brought in not only individuals, but some institutions. Over on the right, you can see the Bechtel Group and 3D Systems, two very large companies. One, a very old, established engineering services company in the mining industry, and the other, a very new, innovative industry in terms of 3D printing and additive manufacturing. Both of these types of things are all about building out the portfolio of how we get out to the asteroids. So our focus on asteroids as a specific destination and resource, as well as today being the right time to do that, is a good thing to understand. So in opening up the economic sphere of influence, if you you assume that this is a good thing to do and you assume that there are resources in space, you'll quickly come to recognize that asteroids are those resources you'd want to go after, and we'll talk more about that in a few moments. But this is really just so important in terms of the resources that are on them, not only for what we can use them on Earth, but what we can use them for in space. The other thing, in my experience in working at NASA for 10 years and as a student for many years prior on space aspects, is that the technology to go out and explore asteroids actually has existed for quite some time. We've actually used it a couple of times in the past 10 years, visiting 3 different asteroids and orbiting them so far, and over a dozen of others that we've flown by. And this is based off of exploration that NASA and Russia and the Japanese and the Europeans have been doing really for quite a long time now. So the access to the resource and characterizing it is certainly within current technology. And of course, from a business standpoint, this is a huge opportunity. It's not said lightly that we believe that the first trillionaires will be created off of businesses that are based in space and based on the resources and infrastructure that will be in space. So I'm going to switch over and show you a video here now. One of the things that's interesting to recognize is that we've learned about space and about asteroids in particular only relatively recently. So the past 15 years of asteroid discovery, characterization, exploration, identification has really just been tremendous. And as you watch the Earth kind of orbit and go around the sun, you can see little flashes of light and asteroids being discovered. And each of these are growing the population of asteroids. The main belt between Mars and Jupiter is getting more and more dense. And we go from 40,000 asteroids initially 15 years ago today to over 620,000 asteroids that have been put into the catalog. There's just a tremendous amount of resources in the solar system, and we've learned about them only very recently. And the most impressive thing is that of these 600,000 asteroids that have been discovered thus far, 10,000 of them are relatively near to the Earth. These are the so-called near-Earth asteroids. And an even more impressive fact is that half of those, 5,000 asteroids that I can tell you the name and the orbit and the location of today, are easier to retrieve materials from than it is to retrieve materials from the surface of the moon. And this is because of the gravity that is on the moon. Asteroids you don't have to land on, you dock with them. We've also learned in combining this with planetary science and astronomy of the resources that are on asteroids. We have come to know that the platinum group metals, ruthenium, rhodium, palladium, osmium, iridium, and platinum are several hundred times more abundant on asteroids than they are in the most productive mines here on Earth. And platinum, of course, is useful for all sorts of things. It's not only valuable because it's rare here on Earth, but they're an excellent set of elements with wonderful properties. After the platinum group elements, and perhaps leading to them, are the structural and industrial materials, things like iron, cobalt, and nickel. And iron on Earth we often think as of an 18th century type of metal that we don't use much anymore. Of course, it's the basis of steel. But this natural stainless steel that exists in space in refinery grade kind of status on asteroids is going to be the material that we build large structures out of space. We won't be shipping raw materials from Earth. We'll be using the iron, cobalt, and nickel that is present in space as a structural material to build large structures and other objects that we need in space. And what enables all this, and what is our first and primary focus today, are the volatile materials on asteroids. The 4 elements, hydrogen, carbon, nitrogen, and oxygen, and the molecules that they form, from water to methane to ammonia. These are radiation shielding, fuel, industrial, solvents, and these are really the gateway to opening up space. And we'll speak a little bit more about this as we go on. A few comments on radiation shielding. For example, on voyages to Mars, often talk about the long duration exposure to space, and not only the solar environment and solar flares, but also cosmic radiation. And the atmosphere that we have and the magnetosphere protects us, of course, from most of this exposure. But once we get outside of that, as humans, we're kind of very susceptible to that environment. And the entire atmosphere and the magnetosphere can be replicated with about a cubic meter of water as a radiation shield. Very low tech, but just kind of bulk mass solution. The problem is, though, is that you need that meter on every side of you. So on above you, below you, front, back, left, right, and of course all the corners, and you end up with dozens of tons per human that you need for a very small living space to be able to protect them from the cosmic radiation which is coming from all directions. So to launch these hundreds of tons of water, of course, would cost billions and billions of dollars, and is not a sustainable thing to do. So this is something that for a permanent presence in space for humans, getting this water from space makes sense. Of course, water is the essence of life and supports all these things. We're mostly made of the stuff. We grow our plants with it. All sorts of manufacturing processes that we use have water as a key ingredient or a key part of the process. But let's talk a little bit about the fuel. And we often think about space in terms of distance. And here, kind of laid out in schematic form, is Earth on the left, Moon, asteroids, and Mars on the right, and then kind of the destinations that your people in space have probably heard about: geosynchronous orbit, Lagrange points, and of course all that stuff on the right is very far away from the stuff on the left in terms of distance. But once you get into space, all those things actually, from an energy standpoint, are relatively close to each other, and we find that the Earth is what is far away. Once you get to low Earth orbit, as Robert Heinlein said, you're halfway to anywhere in the solar system. And this chart kind of demonstrates that point. So our ability to use and leverage and build upon everything that we put into space by being able to refuel it, by being able to get that material that we need to construct in space, our goal long term is to ship as little as possible from Earth into space, and to leverage everything that we send in towards building out that infrastructure, just like we have been settling and expanding into the corners of the Earth right here. So from a resource standpoint, speaking about the water, a 75-meter CI-type carbonaceous chondrite, if you were to extract the hydrogen and oxygen from that, has the equivalent of all the hydrogen and oxygen that was necessary to fuel the entire U.S. space shuttle program, all 135 space shuttle launches. And a 75-meter asteroid is a relatively small asteroid. And with half of all of the asteroids in the solar system believed to be carbonaceous of one type or another, there's just a tremendous amount of fuel out there. And imagine what we would have been able to do had we been able to refuel the space shuttle when it got on orbit so that we could take it somewhere other than low Earth orbit. When we take that capability and extend it to accessing the strategic and precious metals, we look at a little bit larger, about a 500-meter platinum group-rich asteroid. That actually has the possibility of containing all of the platinum group metals that have been mined in history, or the equivalent of that, in the history of humanity. And of course, we've learned from things like aluminum in the 19th century. Aluminum used to be the scarcest metal on the planet. It was very difficult to extract it and to purify it. And in the United States, when we finished the Washington Monument in Washington, D.C., we were so proud of our achievement that we wanted to commemorate it by capping it with a pyramid of pure aluminum. And in France, Napoleon Bonaparte, when he held court, he, of course, served his own court on the finest dining ware that was available, the gold, the china, those types of things. But when the kings and queens visited, Napoleon served them on dishware made of pure aluminum. And of course, aluminum, in the next several decades, we figured out how to extract it from bauxite, and it became extremely abundant. Our computers are made with it, our phones are made of it, we build structures out of it, we fly through tubes of it in the air, we build spaceships out of it. Aluminum is one of the most useful metals that we have, and as it turns out, one of the most abundant metals in the crust. It was merely a matter of access. So imagine what the world would be like if we had access to really as much platinum group metals as we would need. This really can completely change the dynamic, and instead of making money off the scarcity of platinum, we can make money off the abundance of it and all of the applications that it'll enable. So how do we know so much about asteroids, and how can we be so confident that these materials are out there? And the answer lies in the meteorites. Meteorites, as you know, are those things that streak through the sky at night, and we find a lot of them after they've landed on the ground. These, by their very definition, are near-Earth asteroids because they're crossing the orbit of the Earth. And to date, we've analyzed in laboratories across all the different scientists through time about 50,000 different samples of meteorites, everything from metallic iron, nickel asteroids to the palladites to the stony types and the chondrites and the achondrites. And we have a very detailed understanding of precisely what they're made of, and have been able to use that understanding to put together theories on how the solar system formed and where these populations are and how they evolved over time. And we can combine that with our knowledge from space missions and astronomy. And here is a sampling and a graphic to scale of all the different small bodies in the solar system. The comets are in the lower right. We have Lutetia in the middle. Gaspra, Ida, Matilda, Eros, we went into orbit around about a dozen years ago. And I always like to give people a good reference for scale and bring in the Death Star 2, so you know just about how big these things are. Of course, you can remember the equatorial belt there and loop going through, so it gives you a good idea that these things are all different sorts of scales. So let's focus in on Itokawa, which you can barely see right there. Itokawa was a near-Earth asteroid, the smallest one that has been visited by robotic spacecraft so far, by the Japanese in the mid-2000s. And Itokawa has a surface area about the size of Vatican City. And this, from a mining standpoint, actually is a relatively large asteroid. Itokawa has been determined to be an LL4 or LL chondrite, which means that the metal fraction in it could be very platinum group metal rich. But the interesting thing looking at this asteroid through the eyes of an asteroid miner is you can start to think, how would I process this asteroid? If I had technology that required bringing back a large sample, you can see kind of every orbit around it here. There's many large objects protruding from the surface, and perhaps we could latch onto those and remove them from the surface. If we wanted to work with regolith or fine material, you can see that even on a very small body like Itokawa, gravity has actually grain size sorted the regoliths so that the fines have kind of ended up in the lowest potential spot for the gravity here. So these are the type of things that we need to go and visit many more of these and learn more about them as potential ore bodies to advise which ones make the most economic sense to develop into mines. But of course, the other part from asteroid mining, and as people might be familiar from just this year, back on February 15th in Chelyabinsk, Russia, there was the bolide that came in that was very well documented. And this is an example where we cannot prevent hurricanes or floods or tornadoes or earthquakes or tsunamis or hordes of locusts, but we do have the technology today to detect and deflect these hazardous asteroids. And our ability to develop asteroids as resources has the inherent capability of developing the ability to do something about the dangerous ones. So this is a very nice side benefit. So let's go into the technology for a little bit. So you get that there are a lot of resources on asteroids. You get that we understand where they are and that we can know that with confidence. But what do we do about it specifically? And like any mining project, it's a multi-phase. So as I said before, we're focused on characterizing them. Our first commercial mining goal will be to extract the volatiles and to provide a network of fuel depots, both in Earth orbit as well as throughout the solar system where it makes sense to do so. And with that infrastructure, then we can take on the next challenges of the strategic and industrial and precious metals. So our development strategy has been one that I like to think is appropriate for today, for 2013 and the years coming up to us. You've probably heard about exponential technology, and we'll talk about examples of that shortly. But cost of space missions is all about people. We don't bundle up money and send it into space. that money goes into salaries and infrastructure and spending time on things, and the size of the teams that have to do these very complex and sometimes risky missions. So our primary goal with Planetary Resources has been to create a world-class but very small startup mentality team, so that with a minimum of people, maybe no more than 50 or 60, we can do what it used to take a large government team to do, more than 1,000 people, to send these probes out into the solar system. We're also, as I said, diversifying and not just taking aerospace talent, but getting the best talent there, but recognizing that much of the innovation in the world has not come from the aerospace sector recently. It's come from consumer microelectronics and internet and medical devices and even the automotive industry. So we're really looking broadly to find the most talented people out there, get them to our team, and give them the authority to make this mission happen. Like SpaceX, we're adopting a mindset of vertical integration. And what this means is taking the capability to have raw materials come into our facility and have the other end spacecraft come out, so that we are not buying a lot of stuff from other expensive aerospace providers. And we're also able to use that to really optimize what we need for our devices, for our ARKYD probes to go out and prospect asteroids. As I said in the introduction to this chart, we see the acceleration of technology like the Singularity University does, and of course with Peter Diamandis as one of our co-founders. This is a tremendous opportunity to see the future of things and to prepare ourselves for that future. Maybe we don't have the technology today to have fully autonomous robotic mining capability that can run without intervention from humans in processing the materials for mining an asteroid. But I think that in developing that and scaling this up for an industry, there is no question that in 10 years or 15 years or 20 years, as these things get to full capacity and are serving a well-established industry, that autonomy is a natural conclusion. So we need to assume and also plan for an architecture that takes that into account, not just assuming that it'll miraculously happen, but recognizing that there's a roadmap to get there. I often talk about cruise control in automotive. So the car, of course, was invented turn of the century, and in the mid-50s, we added in the cruise control so that we could go at a constant speed when we're going through the highway systems. And then more recently, in the 90s, we added a technology called radar, which kept you from running into the car behind you if you were depending on the cruise control a little too much. And in just the last 5 years, Google has created a self-driving car as well as other people. And these cars are licensed to drive in the United States, in the state of Nevada. So this has been a tremendous rate of progress in that particular area of autonomy. And this is something that we certainly can apply in asteroid prospecting and mining. We use that to turn as many things in asteroid mining as we can into an information technology. Rather than sending back the raw data over millions of miles back to the Earth for humans to interpret, we want to do as much as possible at the asteroid to send us back the conclusion. Tell us what you found. Don't give us all the raw data. Allow the spacecraft itself to do some of the big data aspects, and this helps us towards autonomy. When I transitioned from being an aerospace engineer for the government working in space, I was very familiar with the cost of exploring space, and to point 5 here, I was not too familiar with the cost of exploring the Earth. What we do to find new resources, to develop those, to pull the permits and deploy things to the far corners of the Earth. It's actually quite possible for us to make prospecting an asteroid on par with, if not cheaper, than prospecting resources here on Earth. And this is something that would not have been possible 10 years ago, but today it is, and this is something that we can leverage. And last, and this is a fundamental part of our strategy, we are not pursuing something that we have to wait a decade or more before we return a resource to market to ever make money. We actually are making money today. We've been a profitable company since a few years after our founding, and we're constantly focused on the innovation that we're creating and how we can leverage that innovation to solve other problems that are independent of asteroid mining, whether those be NASA's exploration challenges or the Defense Department or other private customers. There's a lot of demand for the types of innovation that we're creating, and that's an opportunity for us to both deliver things into those markets as well as to leverage them to help our own roadmap. So in pursuing this, we're creating the ARKYD series of prospecting spacecraft, and the science geeks out there have maybe read the story about what the origin of the name ARKYD. This actually is a derivative of the name of the company in Star Wars that created the Imperial probe droids in Empire Strikes Back and the ice planet Hoth. But for me, it's drawing inspiration from the 1960s and the Apollo program, in that when President Kennedy said land a man on the moon before the end of this decade, we didn't go out immediately after that speech and start building the lunar lander and the Saturn V rocket. We had just barely gotten robots into space. We'd just gotten a human for a brief trip into space. And what started in the 60s was a program. And that program started with Ranger, where we tried to get high-resolution images of the surface of the moon so we knew what we could design to. And then with that information, we put orbiters around the moon, the lunar orbiters, a number of spacecraft. We used those to help us soft land on the moon with the surveyors. And then we had very detailed confirmation of the surface of the moon, which then, as in parallel, the Mercury, Gemini, and Apollo programs could use that information then to make the vehicle that would allow us to land on the moon in July 20th, 1969. So in the exploration of asteroids, we see it very similarly. We have a very good idea of asteroids, thanks to the investment of government and the different programs that have gone on over time, and we can use that knowledge to create what is a cost-effective business and a commercial way of exploring many more asteroids to find the right resources. And we look at this as a software release cycle, to where you could look at the 300 series as version 3.0. And we're not going to have all of the versions when we start off in version 1.0. We'll have some of the basic capability. But the idea is we can kind of, through time, have a release cycle. We can test these things in Earth orbit. We can adapt with the times and with the technology. And this is something that we can do very quickly over the next several years, so that maybe as soon as 2016 or 17, we are going out to our first asteroids and prospecting and developing them. And by 2020, going back to the most promising asteroids and starting experiments to extract some of the volatiles on them. So this is just a little illustration. This is part of a concept of operations video, which is on our website and also YouTube. But it is about a little bit of a change in paradigm of how exploration can be done. All of our exploration to date has been by sending a perfect, as best as we can make it, as reliable as possible, very expensive spacecraft. Curiosity is a wonderful technological achievement. It's incredibly complicated, and it's doing amazing things on Mars today. Except that it's a $2.5 billion mission, and that $2.5 billion mission was not tolerant to a launch failure. If the Atlas V that it launched on was not successful, NASA would have been without an option. That $2.5 billion would have been for naught. And the same thing goes with the $8 billion James Webb Space Telescope. So just for launch, it makes sense to distribute your options, like the Spirit and Opportunity missions that I worked on. But if you take that one step further and create multiple copies of things, as this animation shows, you now have the opportunity to do a new style of exploration of an asteroid. Not only can I diversify the risk of any one of these things failing, kind of like blade servers failing in cloud computing, I can also use those individual assets in different ways. One of these, as you see in the upper left, is a optical comm or laser communications relay back to Earth, and all the others are using near-field Wi-Fi communication to talk to each other and to relay that information. We can use multiples of these to explore the asteroid very quickly. And some of the favorite and most interesting things that I have really start when we get a comprehensive view of the asteroid. And now what we can do is we can do what the NEAR mission did, the NEAR Shoemaker mission at Eros. We can do what the Hayabusa mission did. And we can take one of our spacecraft and use it as a geologist's hammer. Empty out the fuel tank, run into the asteroid, disturb that pristine material, and in doing that, reveal essentially and go through a state change of the asteroid that will give us simpler ways of understanding something underneath the first millimeter. And despite the billions of dollars that we have invested in asteroid exploration so far, we've only been looking at that outer sheen of the asteroid, and we really need to look one step further. So this is happening right now. Our team near Seattle, Washington is working on the ARKYD 3 and the ARKYD 100 series space telescope. You can see me here with the spacecraft in our clean room. This is a full-scale prototype that we've built, and its purpose is to take that very large optic, that gold tube that you see there in the pictures, and get that out to the asteroid. We're going through various prototyping stages on this, trying to figure out how we can make these as cheaply as possible, how we can scale up so that we can make dozens of them, and how we can test them most effectively in Earth orbit. In doing that, when we get them into Earth orbit, we'll use them as somewhat of a remote prospector. The wonderful thing that we have with near-Earth asteroids is that we can see them. There's just the vacuum of space between you and the asteroid, and we can actually know more about an asteroid before we go to it than you can know about an ore body a kilometer below your feet here on Earth. So through spectroscopy, through astrometry, and through doing things like photometry, we can take light curves and narrow down our target list before we ever go there, so that we have a much higher probability of getting to the types of asteroids and the specific resource-bearing asteroids that we want to use. And these are just some examples of those different types of things and what we'll be able to do on orbit. Next summer, we are launching a prototype of our core technology called the ARKYD 3. This is another thing you can look up on Wikipedia. ARKYD 3 is another Star Wars reference. This demonstrates all of our core technology in low Earth orbit next summer through a launch that we're working with NanoRacks deployed from the International Space Station. And we're taking kind of this back end of the telescope, all of the brains, and we've repackaged it into a 3U CubeSat form factor. And we're testing out the things that we're building on our own, the star trackers, the reaction wheels, the avionics, the power systems, and then the other things that we're buying off the shelf as commoditized hardware, like the IMUs and the batteries and those things. And with our recent successful Kickstarter campaign, we're also testing out some elements of that. The selfie cam, which you can see here, the context boom, and the display are also on the spacecraft. And these are things that just little by little we can make progress in doing real hardware that has a commercial relevancy to deep space missions and helps us scale up our process. Along the way, we're doing some interesting things that involve more people around the world who are very excited about our mission. Coincident with our Kickstarter, in June we launched the Asteroid Zoo. This is a citizen science crowdsourced way to improve our ability to algorithmically detect asteroids. Our goal is to take the algorithms that we create through this crowdsource activity and run them on our spacecraft so that, like we said, we can turn this into an information science and send just back the information that we're interested to and not all the data. So this is something that we should be launching early next year, and people will be able to help us identify and really curate this rich data set from the Catalina Sky Survey. And I've mentioned it a few times, but in June we ran an experiment, and it turned out to be a very successful experiment. We wanted to see to what extent the public was interested in an outreach program, something that would allow an unprecedented type of engagement with a space mission. We're going to give people the ability to directly point and task our spacecraft for astronomical observations. We're going to give people the opportunity to place this in the hands of classrooms, so you can have it as a STEM education classroom opportunity and learn how science and remote sensing and observation really works, not the way that it's portrayed on TV and in the movies. And then lastly, as about 16,000 of our backers did, we've got the space selfie, and this is really a very simple way to just connect people with the cosmos, being able to take a memory that you have or an experience, to display it on an external screen on our spacecraft orbiting the Earth, and to capture a picture of that and transmit it back to you. People are very excited about this, and one of the top 25 Kickstarters of all time. and the most successful space Kickstarter. So it was good to verify that we indeed had a strong interest in people engaging with our mission. But also, we now have a community of nearly 18,000 people that we can take along with on the journey. And really, this is just the beginning. We anticipate that we'll continue to do this as we go on our exploration mission. I want to wrap up bringing this back to mining and the idea of how we could possibly mine an asteroid. And I'll tell you today that we don't know today exactly how to do that. But in 1980s, when Shell Oil realized that there was oil offshore in the deep ocean, they didn't know how to do it either. And through the investment of a considerable amount of money, they were able to go through a very corrosive environment, through hurricanes and currents and huge pressures, the bottom of the ocean, and then through miles more of rock. And they were able to solve that problem in a relatively short amount of time because, of course, with that investment of money, there was a tremendous amount of additional money that could be made. And in space, I think it'll be exactly the same way, demonstrating that these resources that are out there, that they really do exist in a very specific way on specific asteroids, and to be able to leverage that as the emerging space industry comes to fruition. Space will kind of see that similar acceleration, and it's this type of economic exothermic reaction that will really create a sustainable exploration capability in space and lay the groundwork for every other industry in space that will form. In closing, what we're creating essentially is the crossroads of space. In the United States, when we settled the West, St. Louis was the westernmost point of civilization for a while. It was on a great river for transportation, but beyond that was just kind of uncharted wilderness. And when you went through St. Louis, you stocked up on your rations, you sent your letters, you exchanged everything you had, and then you set out into the wilderness. And that's somewhat what we see as cislunar space and the Lagrange points. That's our St. Louis in space. And the mission of Planetary Resources is to make sure that future travelers and future businesses can stock up and have the resources they can do that, so that they don't have to carry everything that they will ever need from the beginning of their journey. They can kind of stock up along the way. So with that little Halloween thing, I forgot to move here. In the United States, we have Halloween in this little pumpkin rendition of our spacecraft exploring an asteroid. And now, Richo, I think we can go back to some discussions and questions and answers. I hope everyone enjoyed that overview.